Hello and welcome to another RLabs tutorial. In some of your modeling tasks, you might need to deal with elements of chance, so this lesson will be dedicated to generating random numbers in R for stochastic models. In this video, I will introduce you to the RUnif, RNorm, RBinom, and sample functions, and in the accompanying video, we will use some of these tools to simulate genetic drift. One way that we can generate random numbers is by drawing the numbers from existing distributions. We won't go into the math behind the distributions here. We're just going to briefly discuss a couple of the common distributions that might be useful for simulation modeling and how to generate random numbers from these distributions. One of the distributions that is commonly used for random number generation in simulation modeling is the uniform distribution. The name of the distribution is quite appropriate because essentially every value between a specified minimum and maximum value has an equal probability of occurring in the distribution. So this graph here, for instance, represents a uniform distribution whereby every number between the minimum value of 20 and the maximum value of 80 has an equal density, an equal probability of occurring. The function in R that allows us to draw random numbers from this distribution is the RUnif function. We simply write RUnif, and then between brackets we specify the number of times that we want to draw from the distribution, i.e. the sample size, and then we specify the range of numbers between which we want to draw. So we need to indicate the minimum value and the maximum value. So here in RStudio, let's try out an example where we want to generate 15 random numbers between 1 and 10. So we would simply write RUnif n equals 15, min equals 1, max equals 10. And we can see that we have 15 numbers here as the output, all of which are between 1 and 10. Now, as always with functions, we don't actually have to name the arguments as long as we list the arguments in the correct order. So this command, RUnif 15.1.10, is exactly the same as the one we just executed up here. We are specifying that we want 15 random numbers selected from a uniform distribution with a minimum of 1 and a maximum of 10. Now note that these aren't the same 15 numbers that we got up here. Every time we generate random numbers within a given session in R, a different set of random numbers will be generated. This applies for all the different random number generator functions that we will see in this video. As usual with functions, there are default values associated with the RUnif function, and these default values are a minimum of 0 and a maximum of 1. So this command produces 3 random numbers between 0 and 1, but so does this command, because R assumes that the single input value is the desired sample size and that you want the minimum and maximum values to be 0 and 1 respectively. So that is a very basic introduction to sampling random numbers from a uniform distribution. Another common distribution that you might want to sample from in your simulation models is the normal distribution or Gaussian distribution, which is actually probably the most well-known and most commonly used distribution in statistics. This distribution has the classic bell curve shape which applies to many phenomena in life. As you can see in the normal distribution, the majority of cases occur at intermediate values and relatively few cases occur at extreme values. Now the exact shape of the distribution is dictated by the mean of the values, in this case the mean is 0, and the standard deviation, in this case the standard deviation is 1. So with different mean and standard deviation values, the general bell curve shape of the distribution will remain the same, but the width and height of the curve, as well as the position along the axis, will change. In terms of generating random numbers from this distribution, the function is RNorm. So we simply write RNorm, and then between brackets we specify the number of values that we wish to draw from the distribution, so the sample size, then the desired mean of the distribution, and the desired standard deviation of the distribution. And obviously the extreme values are less likely to appear in your sample than these common intermediate values here. So let's try an example. Let's say that we want to draw 10 numbers from a normal distribution with a mean of 50 and a standard deviation of 100. Well, we would simply write RNorm n equals 10, mean equals 50, and SD equals 100. And here we have our 10 numbers. Now again, we don't have to name the arguments within the function. It still works if we simply input the values in the correct order, like this. Now, as was the case for the RUnif function, there are also default values associated with the rnorm function, and these default values are a mean of 0 and a standard deviation of 1. So if I wanted to generate 5 numbers from a normal distribution with a mean of 0 and a standard deviation of 1, I can execute this code here, rnorm501, and we get the results that we want. Or I can simply write the command rnorm5. And R will take the 5 to be the desired length of the sample that we want to create, and then we'll assume that we want the mean to be 0 and the standard deviation to be 1. And it's as simple as that. That's how you draw random numbers from a normal distribution. A third distribution that you can use to generate random numbers is the binomial distribution. There are some major differences between the binomial distribution and the normal distribution, but in case you want to visualize the distribution, at high sample sizes, the binomial distribution is approximated quite well by the normal distribution, so the classic bell curve shape. Now, using this distribution to generate random numbers is a little bit different than the other two cases that we examined. It involves generating the number of successes of independent trials. So here's the general function. We say R binom, and then between brackets we have 3 arguments. The n argument is essentially the number of replicates or experiments, if you will. The size argument indicates the number of trials in each experiment, and then the prob argument indicates the probability that each trial is a success, the only other alternative being failure. Then the output is a vector of length n. So essentially for each replicate or each experiment, the number of successful trials is calculated and reported. Now this is probably best understood using an example. So let's just scroll back to RStudio here. And let's say that we are tossing an unbiased coin 100 times in a row and counting how many times the coin lands on heads, which we will define arbitrarily as being a success. We do this once a day for a week, yielding a total of 7 experiments. So here's the code that can represent this situation. Our binom, n equals 7, size equals 100, prob equals 0.5. So we have 7 experiments, 100 trials per experiment, and a 50% chance that each trial will be a success, i.e. will be heads. And you can see that the output is a vector of length 7. There is one element for each experiment, showing the number of successes for each experiment. And unsurprisingly, you can see that most of these numbers are close to 50, meaning that approximately half of the time the coin landed on heads and the other half of the time the coin landed on tails, which is what we would expect when flipping a coin many times. And just to reiterate, we can see that there is no need to name the arguments when calling the function. We can simply input the numbers, 7, 100, and 0.5 in the correct order. And those are pretty much the basics of the R binom function. Now, just so you know, there are many more distributions out there, and in most cases, there is a corresponding function in R that allows you to sample random numbers from each of these distributions. Now, so far, we've been sampling from existing distributions, but we can also sample from custom-made selections using the sample function. So I'm just going to start right away with some examples to show you how the sample function works in R. So let's say, for example, that we have the numbers 1 to 10, and we want to randomly select 5 numbers as a sample from this larger group. Well, all we have to do is type out sample, and then between brackets we indicate the vector 1 to 10, followed by the number of values that we want to sample from the vector, so 5 in this case. And you can see that we get 5 numbers between 1 and 10 as the output. Now notice that none of these numbers are repeated twice. So R randomly selected one number from a list of 10, then randomly selected another number from the remaining 9, then randomly selected a third number from the remaining 8, and so on and so forth. Now we can also specify the vector outside of the function as well, like this. So we say population gets 1 to 10, and then sample from the population vector 5 times. Also note that the vector does not need to be sequential. It can be made up of any numbers that we want to, like this for example. This is by no means a sequential vector, and we can still sample 5 numbers from this population vector. And it doesn't even need to be a vector of numbers. We can use characters as well. So here our vector is made up of letters from the alphabet, and we can sample 5 of these letters. Now, so far we've been working with examples where the sample size is smaller than the population size. But what happens if we want the sample to be larger than the population? So we want the possibility of selecting the same element more than once. Well, let's try that. Here's our population vector of length 10, just to remind you what it looks like. And we want to sample 15 elements from our population vector, but it looks like that's not possible. But what we can do is alter the replace argument. The default in R is replace equals false. This means that the elements cannot be reselected after being sampled once. So without specifying the replace argument, R assumes that we do not want to replace the elements. But if we alter this argument and indicate that replace equals true, then we can indeed generate larger samples than the population. Now, when might this come in handy? Well, let's simulate a coin toss, for example. We can make an options vector containing the characters heads and tails, which are obviously the two options that we have when flipping a coin. And next we can use sample to simulate tossing the coin 10 times. And we can observe the outcome of each toss. Now obviously here we would need to specify that replace equals true, since either heads or tails or both are going to arise more than once if we are tossing a coin 10 times. And there you go, those are some of the basics of the sample function. Thanks for listening to this RLabs tutorial video. If you found this useful, you might be interested in our free online Moodle course, or check out and subscribe to our YouTube channel.